Hi all, for 6.2 we are looking at the binomial probability distribution. Our objectives include determining whether a probability experiment is a binomial experiment, computing probabilities of binomial experiments, computing the mean and standard deviation of a binomial random variable, and then graphing a binomial probability distribution. We start with determining whether a probability experiment is a binomial experiment. Any definition? The binomial probability distribution is a discrete probability distribution that describes probabilities for experiments in which there are two mutually exclusive outcomes. So we have some criteria for determining if an experiment is binomial. An experiment is said to be a binomial experiment if it meets these four criteria. The experiment is performed a fixed number of times. Each repetition is called a trial. 2, the trials are independent. This means that the outcome of one trial will not affect the outcomes of the other trials. For 3, each trial, there are two mutually exclusive outcomes, success with a big S and failure with a big F. And for 4, the probability of success is the same for each trial of the experiment. Note here, the random variable x represents the number of successes in n trials of a binomial experiment. Here, x is then called the binomial random variable. So for 1, we have a couple options. Do the following probability experiments qualify as binomial experiments? For A, we have a basketball player who historically makes 80% of his free throws, is asked to shoot 10 free throws, and the number of free throws made is recorded. So if we're looking at our 4 criteria, we have an n equals 10 here, so we have a fixed number of trials. For 2, we needed our free throws to be independent, so they definitely are, right? What happens on the first free throw is not going to change what happens on the second, so each free throw is independent. For 3, we were looking for those two outcomes, so our success here would be he makes the free throw, and our failure here would be a miss. Those are our two outcomes. And for 4, our probability of success remains the same on every trial, so that's true here. Right, he's got an 80% chance of making any shot, or each shot, however you want to phrase it. All right, for B, we have a basketball player who historically makes 85% of her free throws, is asked to shoot until she makes 5 in a row. So I made this one nice and quick so you don't have to go with my writing. Hopefully you can see for number 1, we don't have an n, right? So we do not have a fixed number of trials. So not binomial, right? We're just going to keep shooting and tracking until we make 5 in a row. All right, for computing probabilities of a binomial experiment, we start with a note. We'll use technology for our computations, but understanding notation and identifying values is important. So we have some notation for binomial probability distributions. There are n independent trials of the experiment. So n is still our sample size, or our number of trials. We let little p denote the probability of success for each trial. Then 1 minus p is the probability of failure. You'll also see, if you look it up a lot of places, q is 1 minus p. And we let x denote the number of successes in n independent trials. So our values that capital X can take are little x's between 0 and n, right? From no makes and the free throws to made all of them sort of thing. Note here, the probability of success, little p, is always associated with the number of successes, capital X. So we want to make sure our makes and our probability of makes or success go together always. For 2 then, a basketball player who historically makes 80% of his free throws is asked to shoot 10 free throws, and the number of free throws made is recorded. So we're working off that same setup that was binomial. For A, we want to know the probability that he makes all 10 free throws. So if we do, think of it this way, we want the probability that x is 10, right? He makes all 10. But that's really the probability that he makes the first, and makes the second, and all the way to and makes the 10th. Right, so we want him to make all 10 of the free throws he takes. This is our independent multiplication rule, right? We talked about all those shots being independent. So really it's the probability that he makes a shot to the 10th power, which is going to give us a 0.8 to the 10, or approximately 0.1073. So we can say that we expect him to make all 10 shots or free throws in 1 out of every 10 trials. All right, we're pretty close to a 0.1 there. If we did want to go, we could say 107 of every 1,000 or 1,073 out of every 10,000 trials, but about 1 in every 10. What's the probability that he misses at least 1 free throw? So really we're looking for our probability that x is less than 10. And we don't have a way to say we're tracking the number of misses, but really this is the same as saying, let's do it in words, he misses at least 1. So this is our at least probability. Really we're going to compute it with a 1 minus the probability that x equals 10 that we just looked at. Right, so instead of 10, he could make 9, 8, 7, 6, 5, 4, 3, 2, 1, or 0. Right, he misses at least 1. So we get a 1 minus 0.1073, which comes out to a 0.8937. And we can say we expect him to miss at least 1 shot in about 89 of every 100 trials. Right, so just look into that second decimal place for looking out of 100 there. All right, note for cases where it's not all or nothing, we'll rely on technology to speed up the process. Let's look at a tree diagram to learn why. So for 3, we have suppose a coin is flipped 4 times. The sample space would be, we'll draw out that tree diagram like we've done at least once before, but our first flip can be either heads or tails. On our second flip, we can get either heads or tails, regardless of what the first flip was. On our third flip, we can still get either heads or tails from each of those flips. Right? Nothing we did before is going to affect the third flip of our coin. And if we go one more time, we can go heads or tails down here for our fourth flip as well. For that fourth flip, no matter what happened before. All right, so our sample space S then, if we follow all those branches of the tree, we could get heads, 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 heads. Or we could get heads, 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 and then tails at the end. We could get heads, heads, and then tails, heads, following that third branch down to the tail. And then we could get heads, heads, tails, tails. Now we're starting on the other side with heads and then tails. So heads, tails, heads, heads we could go down. We could go heads, tails, heads, tails. We could go heads, tails, tails, heads. And to finish off that left side, we could go heads, tails, tails, tails. I'm going to show the first one from the right half, tails, heads, 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 because it's the last way that we can get a single head in our trial, or a single tail in our trials, along with those 3 heads. And so what we're seeing here with this tree, there are 1, 2, 3, and 4 different ways. So 4 ways for 3 heads and 1 tail. So if we wanted to compute that probability, heads, 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 tails, or 3 heads out of these 4 flips, we couldn't just do the 1/2 times 1/2 times 1/2 times 1/2, which would give us 1 out of 16. That would only account for the probability of any one of those. Right, so all 4 of these with the checks now would have a probability of 1 out of 16. So if we add those up, we'd see a 4 out of 16 or 1 out of 4 chance of ending up with 3 heads. And so when they are small distributions, we could write out our x's and our p of x's to get our probabilities. we could get 0, 1, 2, 3, or 4 heads if we flip 4 times. And it's going to be a 1 out of 16. There's only one way to get all heads or no heads, right? Meaning you'd get all tails. We just looked at a 4 out of 16 for getting 1 and 3. So 4 out of 16 for 1 head and 3 tails, or 3 heads and 1 tail. Let me throw a number of heads here so we're not confusing that. And then to make this add up to 1, we have 4, 8, 9, 10 out of 16. So we'd have a 6 out of 16 probability of getting 2 heads and 2 tails. All right, so instead of trying to look at all this and adding up different probabilities, we've got a binomial calculator on StatCrunch that we're going to use. For 4, in a recent poll conducted by the Bradley Corporation, it was found that 64% of adult Americans operate the flusher of toilets in public restrooms with their foot. Suppose a random sample of n equals 20 adult Americans is obtained, and the number x who flush public toilets with their foot is recorded. We want to verify this is binomial before we start. So we have an n equals 20 here, which gives us that fixed number of trials. For 2, we are choosing from all of the adult Americans, so this random sample, random adult selected, treats them all as independent. For 3, we have our success. That would be flush with foot. Or our failure would not flush with foot. And for the 4th one, our probability remains the same. So our probability of success, we could go little p there, is 0.64 for each person. And so that's not going to change. B, we want to find and interpret the probability that exactly 12 flush public toilets with their foot. So we want the probability that x equals 12, knowing that n is 20 and p is 0.64. So those 3 things are all we need. So we can rewrite our probability that x equals 12 over here. So we can write our answer and then compute in StatCrunch. We want to go to Stat, Calculators, and Binomial to do our binomial probabilities. And then we can sub in whatever we have on our calculator. Our sample size n was 20. Our probability of success is 0.64. Our n, our x, our makes is 12. We want to be exactly equal to 12. And then we can compute. We get a 0.1678. So we can say in, let's just go all the way, 10,000 trials, we expect 12 people to flush with their foot in about 1,678 trials. For C, we want to find and interpret the probability that at least 16 flush public toilets with their foot. So we want the probability that x is greater than or equal to 16. And so this is the nice part about StatCrunch. If we have more problems with that same setup, we can just put in our 16. We're going to put in our greater than or equal to, right, at least 16. And we get a 0.1011 for our probability. So we can say we expect at least 16 people to flush with their foot in about, let's just go the 1 of every 10 trials again, because we're really close to 0.1 there. All right, for D, we want to find and interpret the probability that between 9 and 11 inclusive flush public toilets with their foot. So we can go back here. We can use this between calculator. We just want to change it to 9 and 11. And we can compute. So we have 0.2436 for our probability there. So our probability that 9 less than or equal to x less than or equal to 11. So between 9 and 11 inclusive. That's why we have that equality. And we had a 0.2436 there. So we can say we expect between 9 and 11 to flush with their foot in about, let's go 24 out of 100 trials. And so we're just picking out that decimal, going as many zeros as we need to get to that decimal place out of 10, 100, 1,000, 10,000 trials. For E, we have, would it be unusual to find more than 17 who flush public toilets with their foot? Why or why not? So our probability of X being greater, strictly greater than 17, right? More than 17. We can go back to our standard calculator, put in the 17, and change it to strictly greater. And we'll compute a 0.0096 there for our probability. And as we have done with probabilities before, we would say, yes, this is unusual because our probability that X is greater than 17 is less than 0.05. All right, we move on to computing the mean and standard deviation of a binomial random variable. Note here, the same formulas for computing the mean and standard deviation of a discrete random variable can be used, but easier formulas exist to find the mean and standard deviation for a binomial experiment. Our mean or expected value and standard deviation of a binomial random variable are a binomial experiment with n independent trials and probability of success little p has a mean and standard deviation given by the formulas. Our mu sub x is equal to just n times p. And our sigma sub x, that standard deviation, is given to us by the square root of n times p times 1 minus p. Or again, you might see that as an n times p times q, where q is 1 minus p. But for 4f then, we want to find the mean and standard deviation for the flushing experiment from above. So our mean there is going to be our n was 20 times our 0.64 for our probability. And that should come out to a 12.8. Our standard deviation for that random variable, or binomial random variable x. Then we compute the square root of 20 times 0.64 times 0.36 if we subtract 0.64 from 1, and that comes out to approximately 2.1. For G, if the trial was repeated with 300 adults, what number would we expect to flush with their foot? So we're computing an expected value, and we remember that's just the mean of the random variable. Our new n is 300, so we'll write n times p. We got a 300 times the 0.64 this time, which comes out to 192 people. So if we repeated this trial 300 times, we'd expect 192 adults to flush with their foot. All right, for graphing a binomial probability distribution, we have a note. If you were asked to graph a binomial probability distribution, you would first need to calculate the probabilities for each value of the random variable x, and could then draw it with vertical lines up to each probability, as we did for the discrete probability distribution graphs. The binomial calculator, as you've seen though, will do this for you while you're calculating probabilities. So worst case, you'll have to pick out one in the homework, but you shouldn't have to draw anything by hand. If you want to draw some little ones here to learn how p and n can affect those graphs, please do. But for 5, we're going to construct the graphs of binomial probability distributions given the following values and comment on the shape of each. So we want n equals 10 and p equals 0.1 for the first one. So I'll put 10 for n, 0.1 for p, and we can put some value in. Doesn't matter what it is, we just want to compute to see that distribution. So we can see our shape. I'm not going to draw a whole graph there, but we can see a lot of our values there on the left and smaller values out on the right. So we would call this one skewed to the right. Right, we see that tail on the right side. For n equals 10 and p equals 0.5, if we compute, we see a nice symmetric curve there. So we start low, come to a high point in the middle, and then go back down at about the same rate. We call that bell-shaped or symmetric or normal. We can write them all just to remind ourselves. And if n is 10 and p is 0.9, you might be able to guess what's going to happen. But we see small values on the left here and bigger probabilities as we move to the right. So we got some small values over here on the left, and we're getting bigger as we move to the right. So we call that one skewed left. We can see that tail on the left side. Again, look to your feet for the skew. And then we want to do n equals 100 with that 0.9 for p. So we can change our n here to 100 and recompute. We can see that table almost normal, right? So there's a lot more values on there. I wouldn't want to draw out 100 of these, but we can see we're really, really close to a normal distribution. So we can call it approximately normal. That'll lead into our note there. Note, we see two takeaways from the constructed graphs. One, with a small sample size, n, the value for p drives the shape of the distribution. As n increases, the distribution becomes approximately normal. If n times p times 1 minus p is greater than or equal to 10, the distribution will be approximately normal. And we want to know that because if the distribution is approximately normal, we can consider values that are more than 2 standard deviations from the mean to be unusual. And so this is back to that empirical rule. And we're looking at our mean minus 2 standard deviations all the way up to our mean plus 2 standard deviations. So we'll try one example with that to finish off. For 6, the Gallup organization reported that 11% of adult Americans had a great deal of trust and confidence in the federal government handling domestic issues. Suppose a survey of a random sample of 1,100 adult Americans finds that 84 have a great deal of trust and confidence in the federal government handling domestic issues. Would these results be unusual? Why or why not? So we need to start by checking to see if we are normally distributed. So we want to do that n times p times 1 minus p, and we're hoping that's greater than or equal to 10. Our n is 1100, our p 0.11, our 1 minus p then 0.89. That's going to come out to a 107.69, which is greater than or equal to 10, so we are approximately normal. To answer the question then, for unusual values, we need to compute the mean. Our mean is n times p, or 1100 times 0.11, which comes out to 121. And our standard deviation here, our square root of n times p times q, is just the square root of that 107.69 that we found with our check. And that comes out to about a 10.4. And so what we want to see on our distribution, try and draw it on a side so we can fit our answer if we want to as well. We'd have 121 in the middle. If we go 1 standard deviation above that, we get to a 131.4. 2 standard deviations would take us to a 141.8. If we go the other direction, we get a 110.6, and 2 standard deviations out would be a 100.2. So 84 would be unusual because it's more than 2 standard deviations below the mean. And we can say 84 is less than that 100.2, which was our cutoff. So that's it for 6.2. Try some stuff out. Reach out if you got questions.